All right, so Josh with FIMS today.
FIMS. Okay. Hello. Again, I'm showing the same flowchart I showed yesterday just to orient us on our journey. So we're talking about different ways of making dark matter. We began with the famous WIMP. And what I really hope you kind of are beginning to take away from all of this is the WIMP is one idea that, although compelling, is part of a much broader landscape of ways that dark matter could have been produced through particle interactions in the early universe. And so far everything we've talked about has been thermal. So dark matter had rapid interactions, was assumed to have rapid interactions, had a temperature, and its abundance could be calculated based on studying when things went out of equilibrium. And we've sort of now studied each of these different options. So either symmetric or asymmetric, and within symmetric, there's different types of interactions that could give you chemical equilibrium. The WIMP was just one example. The rest of these lectures will be on the sort of other side of the dark matter world, talking about models that are non-thermal, where dark matter does not begin with rapid interaction setting it into equilibrium. And this is will allow for much weaker interaction strengths. But they're very interesting candidates for dark matter that live within here. Tomorrow, I'll talk about ways that the axion can be produced from misalignment. Today will be something that will be non-thermal but closer to thermal, called FIMS. And here the idea will be that although dark matter is non-thermal, its production will be related to the properties of other thermal particles. So this is kind of a good way of dipping our feet into non-thermal before getting to something even more different tomorrow. So now we're going to start to explore this side. Start to talk about FIMS. Okay. So what does FIM stand for? WIMP was weakly interacting massive particles, so a FIMP is deeply interacting massive particle. Okay, and well, there's going to be several assumptions that different FIMP models will have in common. So let me just begin by enumerating the assumptions that we'll make today. And they're sort of opposite from assumptions that we were making in prior lectures. So number one, we will assume that dark matter is kinetically decoupled not only from the standard model, but from anything. So that it does not have a temperature or an equilibrium phase-based distribution. Right. We began by talking about WIMPs where it was, say, kinetically coupled to standard model. Last lecture, we relaxed that and allowed the dark sector, although to be kinetically coupled to itself, but decoupled from us, so it had a different temperature. And now we'll take the extreme view that it's kinetically decoupled from any other states. So sort of any interaction that would exchange energy between the dark matter and other particles that are thermal, we will assume to have rates of energy transfer far below Hubble. Yes.
Can it still have multiple mass states if it's kinetically decoupled from everything?
You can consider multiple dark matter states, but they would be decoupled from each other in general.
Okay, got it.
Yeah.
I guess I don't know what you mean when we say it's decoupled from everything beyond the standard model. I mean, couldn't I have my dark matter get some kind of dark temperature from just interacting with itself?
Absolutely. Yeah, if it has large enough self interactions, it could do that. And here, yeah, we're assuming that's not the case. Yeah.
Okay, so now we're saying.
But you would need, if it only interacted amongst itself, you need to kind of inject it in some way because that wouldn't be able to produce it.
Okay.
But you could sort of have within a dark sector, it could self-thermalize through its own interactions.
Okay, so now we're saying that's not the case, and I can't even define a dark temperature.
Exactly. Yeah, and there will be no notion of temperature for the dark matter now.
Okay.
Yeah, so there's no dark temperature describing the state. Yeah.
Yeah, I guess I'm wondering traditionally why we like we assume that it actually like not the case, so that dark matter is kinetically coupled and chemically coupled. Yeah, like why sort of that was probably the first approach that we
Choose your path.
yeah, okay, but I mean
They're both possibilities. Yeah.
yeah,
We don't know.
The thermal like interpretation seems to be more popular, like more
Axions are extremely popular and growing, and they're on the other side here.
okay.
Well, thermal has some attractive properties. The standard model was thermal, so if you kind of want to say maybe dark matter is like us, and we can apply the methods we use to understand the standard model's cosmology to dark matter, then there's some sort of similarity assumption. And thermal also has the attractive property that a thermal state washes out sort of any dependence on what happened earlier. So it's very calculable. So the type of models I've been describing are extremely calculable in terms of the interactions that are manifest at low energies and testable in experiments. That's less true for non-thermal cases, where you tend to be more sensitive to initial conditions, less sensitive maybe to what you're measuring in experiment, although there can still be interesting relationships. So, but the flip non-thermal, because it's not, things are not washed out by a thermal state, you can in principle access much higher scales, which is theoretically very interesting too. So it's quite different.
Just to make sure I'm crystal clear, this phi can even be another dark matter, right?
Yeah, just sort of anything. Yeah.
I do not understand why they do not have a temperature. I mean, an ideal gas is also temperature, and they're not correct. They decouple from each other. I mean, the notion of temperature just means that you have, let's say, an ensemble of infinitely many dark matter states. So you can always define temperature.
Sure. Well, I guess more specifically, I mean that it doesn't have the phase-space distribution will be some arbitrary function of momentum and not the equilibrium phase-space distribution that I wrote before, which is only determined by temperature. So the phase space now has sort of an infinite number of degrees of freedom in general. That's a more precise way of saying this, if you want. Yeah, so it's just not going to be the form of F that I wrote before. That's really the sharp statement.
I mean, right like that, that means that it is not internally equilibrium. So in this way, you cannot define a temperature. Is it that way what you mean?
Yes. Yeah, exactly. It's non-thermal. It's not in kinetic equilibrium. Its phase-space distribution is not given by the Fermi-Dirac or Maxwell-Boltzmann phase-space distribution. It's in general an arbitrary function, which is calculable and will be different from those functions, and could have non-trivial momentum dependence. So I don't know what temperature would mean in general for such a distribution.
I mean, temperature just means that if you define a temperature, you are in thermal equilibrium in this case.
Yeah, here you're not.
Regardless of whether they interact with each other or not.
Yeah, indeed, I agree. You can define a temperature for non-interacting states, and usually you do that when they have an equilibrium distribution. So if something in equilibrium decouples while it's relativistic is a classic example, then you will preserve an equilibrium distribution, and you can then talk about it as temperature. Yeah, here I don't mean that. Okay, any more questions?
And are we saying it's kinetically decoupled right at the get-go, or this happens at some later stage?
At the get-go, let's just say, yeah, for everything we'll be talking about. I mean, you kind of always need to specify an initial condition for everything I'll be talking about. So sort of, let's just call what happened before the initial condition. So if there was some prior coupled epoch, I'm just gonna freeze that and call that initial condition. And during all the periods of time I'll be talking about, this will be true. Yeah.
And just a quick follow-up, are the periods of time that we're considering including inflation?
I'm not going to be talking about production during inflation in these lectures. So that's an interesting topic. That would be an initial condition from the point of view of these models. But it is a possible way. Non-thermal dark matter could just be produced during inflation. It could be produced by inflaton decay into dark matter.
Right.
And those will be from perspective of these lectures and initial condition, and that contribution you should add to the types of mechanisms I'll talk about.
Yeah, so I guess just to rephrase my question before, is there like any evidence or what we know about the early history of the universe that would make thermal as opposed to non-thermal candidates like more preferable?
Not in my opinion.
Okay.
I think they're both valid. We only know the energy density
Mhm.
and
Lambda CDM.
Mhm.
I mean, lambda CDM.
the lambda CDM can then be appended with both thermal and non-thermal models of dark matter. So it's sort of going to be equally consistent with data.
Okay.
People may have prejudices, but these lectures, I promise, are without prejudice.
Okay.
Okay. So, yeah, sorry. So I'm going to assume, for sort of simplicity, an initial condition of no dark matter for this discussion. That's normally what's assumed in FIMP studies. But really, like, and it was pointed out, you could have production during inflation. So really, you can think of it as additive and they'll factorize. So I'm going to assume an initial condition of no dark matter, but if you want to add an initial condition of dark matter, you just add that to what we're talking about. So it's mainly to simplify the language, but it won't matter. Yeah, so sort of initially, we will have sort of f chi equals 0 and chi equals 0. And then we will produce it through sort of calculable things that happen at lower energies. Okay. That was number 2. And assumption 3, for these FIM models will be that some reaction slowly produces dark matter. And that's what we would calculate to determine the dark matter abundance. So a reaction slowly produces dark matter. So why do I use the word slowly? That's the only way you can produce it from a reaction that's consistent with assumption 1. So otherwise that interaction itself would kinetically couple the dark matter and thermalize it. So given assumption 1, there's an upper bound on the size of reactions, and that will in general mean that you're adding sort of less than 1 particle per Hubble time. So that's what I mean by slowly. Okay, and then just as in the sort of thermal case, there were many possibilities for the types of reactions that encode chemical equilibrium and chemical decoupling, and I showed you sort of a zoo of them. Similarly, in FIMPs, there are many types of reactions that could play the role of number 3, and then those are sort of differently named models that you can play with, and I'll give you some taste of them today. But for example, it could be produced by scattering. So we label, so here psi will label a thermal state. Here chi is the dark matter, and then phi is maybe something else that won't matter. So here and the assumption is that these will be in equilibrium, for example. And then they annihilate into chi, but this annihilation rate has to be slower than Hubble, or else it would kinetically couple the dark matter. But it still will produce some dark matter, and by an amount that you can calculate using a Boltzmann equation, and then you can match that onto observation. So you can produce it from slow scattering. You can produce it from slow Ks. Or again, psi will label a thermal state, and chi is the dark matter, and phi is something else. You can also actually produce it from oscillations. You have some state psi, maybe it can oscillate into chi. The classic example of this are active neutrinos oscillating into sterile neutrinos, but the sterile neutrinos are not entering equilibrium. Okay, so in each of these cases, there's some interaction that involves the dark matter, and each of these interactions must be slower than Hubble, because if any of those interactions are fast compared to Hubble, they'll kinetically couple it, and then you're back on this side of our flowchart. So, but they still will produce some calculable amount of dark matter. Yeah.
Why are you calling this first example scattering? It looks more like some kind
Oh, sure. Yeah, I mean 2-to-2 process. Sorry, some inelastic scattering words. Sure. Yeah, I'm just using those words synonymously. Okay. And in each of these cases, you can write a Boltzmann equation. And that's kind of the nice thing about FIMP models is you sort of assume the dark matter balance is tied to the properties of other thermal states, and then you can still use the technology that we've been learning in the last 3 lectures to calculate the dark matter, although the dark matter itself is not in equilibrium. So you can still write down a Boltzmann equation. Maybe now is a good time. Since we've already gained some familiarity with Boltzmann equations in the last few lectures, maybe I'll go one level deeper now and tell you the true form of the Boltzmann equation. Formally, really, the Boltzmann equation, I described it as an equation for the number density. That was a simplification so far. Really, it's an equation for the phase space distribution function, which you can integrate to get to number density. For equilibrium, this distinction didn't matter because the phase space distribution had a known form for WIMPs. But for FIMPs, that's not the case, so it's good theoretically to have in mind kind of full Boltzmann equation. So I'll just write it for you. I'm not going to derive it. But yeah, so the phase space distribution of the dark matter will in general depend on its momentum and time, or the sort of temperature of the universe, whatever, age of the universe. And it's the following PDE. It depends on both time derivatives and energy derivatives. Yeah, so it turns out to be the following. That's just Hubble. And if it were inert, then this would just be a 0, and this is just describing how the expansion of the universe affects phase space. This is sort of the redshift. When interactions are happening, then the right-hand side of this is called the collision operator. Okay, and although I didn't write this equation before, this equation actually applies to all of the models we've talked about so far too. And then when I wrote this n dot plus 3hn, it was really take an integral over momentum with this equation, and then you can derive the equation I was writing. So this it's a sort of Boltzmann equation for the phase space distribution function. Yeah, and the number density in general is given, was weighted by the number of degrees of freedom, and then given by momentum integral over f. Or if you want to make the time dependence explicit, this only depends on time, because you can integrate over momentum. Okay, and you can perform a momentum integral over the left and right hand sides of this equation, and then you get the left hand side becomes the sort of thing that's familiar to us so far, and then the right hand side is just an integral over the collision operator. And it turns out you pick up a factor of 2 when you to get this form. This is the Lorentz invariant phase space. And then you can integral over the collision operator. The collision operator is just related to the thermal average. So it's just an integral over matrix element multiplied by phase space functions integrated over initial and final states. So it's and then in the case of 2 to 2, so for example, if we consider 2 to 2 sin, which you can find, then this integral of the collision operator the following function. And it would also have another term for the inverse process. So remember, for the WIM case, we always had 2 terms for the forward and backward. But for FIMPs, you can always neglect the opposite process, but by the assumption, well, if you make this assumption of 0 initial abundance, then your abundance is always, if assumptions 1 and 2 together imply that the abundance is always far below the equilibrium abundance, and then the inverse process can be neglected, and you can just approximate things as being one directional. So if this is a FIMP, it satisfies 1 and 2, then this integral collision operator just takes this form where this thermal average is the type of object that we were discussing before. Yeah.
What about the diffusion curve? Is it usually appearing also on the left side?
I'm not sure what you mean.
I mean, the distribution function is depending on the momentum p, so we would also have something like df over dp times a velocity or a force. I mean, this is the usual.
I think it maybe this definition is pushing it into the collision, because this is only for, I mean, this, if you're just in FRW and you're on an, you're just free falling, then the left-hand side is everything.
I mean, you can also have like free streaming inside the expanding universe, and the free streaming is covered by the diffusion inside. Or
Maybe
is it-
you're adding gravitational perturbation on top of FRW? Yeah, so this is the Boltzmann equation in FRW in the homogeneous limit. Yeah, and indeed, if you want to now like put a galaxy and ask what happens, then you need to do more.
So you have an expanding universe, but you do not have plasma inside that, for example, vacuum plasma, or I don't know. So this is only in vacuum, which is expanding.
Yeah, well, the plasma are the things like F. Yeah, I mean, so it's a homogeneous universe with the gas particles that interact through processes encoded, whose effects are encoded by collision operators. And then if you turn off all cross sections, like send all couplings to 0, then you're just free falling in FRW, and then the left-hand side describes what happens, and the only effect is that your momentum moves redshift. But yeah, this is not the most general form of a Boltzmann equation, which might be what your question is getting at, where you add other sources. Yeah.
Will the collision operator always have units of cross section? Or like 10 units is cross section? Or is that just in that example?
Let's see, it'll have the units to match this side. Yes, this is energy to the 4th.
Which translates to the units of the cross section?
Well, yeah, see, it's number density squared times cross section. Yeah.
Oh, right, I was forgetting that was number density. Thank you.
Yeah, or number density times decay rate. Yeah.
Thank you.
So we've got this process. Could you also have like phi scattering off psi to produce dark matter? So you just switched one of the phi's on the side.
Here's time's going this way for me, so you wanna like flip that.
Yeah.
Sure, in general, yes. So I'm sort of making an assumption here that I'm dominated by one process versus an equilibrium, and I'm kind of not speaking of this.
Right.
But indeed, you should sort of sum all initial equilibrium states that can give a chi. Yeah, I mean, it's maybe more, maybe just put, I mean, an x here, well, the x is that variable. So just take all two processes with 2 states from the equilibrium in the initial, and then one.
So I guess in time, it's like that other state doesn't have to match these assumptions. It's just the dark matter.
Yeah, that state I'm making no assumption about, and it could even be another chi, and then you add a factor of 2.
Right.
So sort of for this lecture, phi is just something I don't want to talk about. It won't in your case, if there were a process where that state could combine with psi, then I would label it one of the psi's. Right. So is that clear?
Yeah, no, that's good.
Okay. Thank you. So yeah, that's sort of a general framework definition. And then before I get to explicit cases, I want to talk about, well, a very important question is at what time or what temperature is the dominant production? So we're assuming some reaction produces dark matter, but when does that mostly happen? And there's sort of 2 different cases that I'll call UV or IR, depending on whether most of the production is happening at high or low temperatures. This is sort of the first important distinction to me. So UV versus IR. This section I want to ask, at what temperature is the dark matter produced? In the case of, say, WIMPs, we started with a large amount and then they depleted when you crossed their mass threshold, and Boltzmann depleted, and then you froze out. So that was sort of when things happened. And now I kind of want to ask the analogous question, when do things happen? I'm going to define gamma of I to be the dark matter production rate. Yeah.
Are we assuming that our only production mechanism is those different, like the scattering and the interactions with the standard model particles?
Well, these they could be standard model or they could be non-standard model. This applies generally.
Okay, but it's
This
only
discussion.
these very slow reaction rates?
Yeah, I'm assuming it's produced by slow reaction rates
Uh-huh.
of states that are themselves in equilibrium. Will be usually the assumption. Actually, sometimes they won't be. Other states, yeah, which could be standard model states would be the minimal case, but it could also be a thermal hidden sector that's evolving on its own and leaking into dark matter. So it could be sort of anything.
So I guess my question is, these reaction rates are happening so slowly, how could we possibly come up with, 80% more dark matter than there is visible matter?
There's not much visible matter. Yeah. You only need, like, if you remember, you want this m times yield to be 1 eV roughly. And yield is about number of dark matter per number of photons. So if the dark matter mass is far heavier than eV, the number of dark matter per photon you need to produce is a very small number. So it's not hard to get. For WIMPs, it's not like it's really why is there so little dark matter, and it's because the Boltzmann suppression allows you to exponentially remove a huge amount. If the mass is a GeV, then you need 1 billion photons per dark matter particle.
Gotcha.
Okay. So this you could do a general with this example. Let's do an example where we assume the dark matter is made by a 2-2 process, and then ask like what types of interactions will give production at different temperatures. So throw the same cartoon. This section of the lecture will be sort of at the back of the envelope level where we're going to use Josh given units. Okay, so the rate of this. So in this case, then the rate is the usual sort of n psi sigma v that we're used to for 2-2. Okay. And now we should ask a little more about what this bubble is. So I'm going to assume this discussion will be within the context of effective field theory. I'm going to assume there's some operator that generates this of some dimension, and then we'll just kind of study the cases of what happens as a function of the dimension of the operator that generates this. So suppose the scattering is generated by operator O with mass dimension D. So if it's 4 or less, then that would be like a marginal or relevant operator. If it's higher, if it's 5 or higher, that would be a higher dimension operator where you need effective field theory to describe it. Okay, so then we can sort of estimate the amplitude of the scattering, which I'll call A. And here I'm just going to use dimensional analysis. Which should be familiar to those of you who've learned the concept of power counting and effective field theory, which if you're a theorist and haven't learned yet, then you should yell at the people that taught you field theory and learn it immediately. Or talk to me at coffee, okay. But here, lambda will be the cutoff of the effective field theory that the operator O lives in. And then the amplitude will scale like this. This is effective, sort of the way to think about effective field theory. So when D is higher than 5, the effect goes away at low energy, and that's sort of why higher dimension operators are hard to see. And if D is 4, then sort of important at all energies, and if D is smaller than 4, then you have a bigger effect at lower energies. Okay. Okay, so this is our DFT cutoff. Okay. So continuing with our dimensional analysis, we're interested in the thermally average cross-section. And let's contemplate the case where we're at temperatures above the mass of the particle that's doing the scattering, but temperatures within the realm where this effective theory is valid, or else this conversation wouldn't make sense. So I'm going to assume that the temperature is in this domain between the masses and the cutoff. And then if we then we can use dimensional analysis to estimate the thermally average cross-section. And it'll have sort of the number of powers of cutoff that we can predict from the amplitude squared. And then the only other scale that's relevant in this domain is the temperature, because that's the dominant scale. So we can estimate from dimensional analysis that this will go like, well, let's see, so first, the denominator, so it's just this squared, so it's going to be lambda to the 2 minus 4. Okay, and then just to get the dimensions right, the numerator will go like temperature to the 2 d minus 4. That is not right on minus 2. Okay, so just that the whole thing is minus 2, like a cross section. So this is just saying at high temperatures, the temperature is the scale that will appear. And this is true if you look at if you explicitly compute thermal averages, then you'll find this, where the T's come from the phase-space distribution function of the initial states. Okay, so now we can look at the dark matter production rate. It goes like n psi sigma v. Can anybody tell me how will n psi scale at the back of the envelope level in this domain? T cubed. Thank you. This is one of the key things that you should have quickly after the last few lectures. T cubed times this now. Yeah, so we'll just jump to the answer. So then I just add plus 3 here. So it's t to the 2 t minus 4 now plus 1. Or lambda 2 d minus 4. Okay, and now well, I should have said earlier. But yeah, so I defined this production rate. But if we want to ask when is the dominant production, we have to compare the rate based on time scale, and obviously that'll be Hubble, because it's the only time scale. So if we want to ask at what temperature is it produced, the dominant production will always be when gamma pi over h is maximal. Again, I'm sorry for going out of order. The reason I wanted to write this here is that this statement applies for any rate beyond just 2 to 2. So this applies to the example, but also more generally.
I just have a small question here, dimensional analysis on sigma here. How did you know that it would have to, this 2 up front of the d minus 4? How did you know that was real?
Oh, well, I'm assuming, yeah, that the cross section goes like the amplitude squared. And that is an assumption. It's actually a good question, because if this thing were interfering with another thing with different scaling, it would be different. So I'm assuming like that this operator generates this process, and it's really this operator squared generating this process to get that scaling. You can generalize it to two operators interfering, and then you have to multiply their respective lambdas. So I'm simplifying to the case that a single operator is doing the business. Okay. Good. So then we want to divide this by Hubble to estimate when the production occurs. And that just means that we divide here by t squared, and then an M Planck appears. So this will go we'll plot the constants M Planck over lambda to 2 minus 4. Now we're at the sort of final temperature dependence. 2 to the t minus 4 minus 1. Okay. So if we want to ask when is the dark matter produced by this operator, it'll be when this is maximal. And then if you just inspect the numerator, you see that there's a different behavior depending on whether d is greater than 4 or not. So the sort of thermal, the evolution separates higher dimension operators from marginal and relevant operators. And I will call IR dominated or infrared dominated, sort of effective field theory language. If d is less than or equal to 4, then we see that this is maximal as t drops. Okay, so then pi over h grows as temperature drops, and then you're dominant, and then the dark matter will be produced at low temperatures. By low, I mean within this domain. We'll see later. It'll actually be typically t of order some mass threshold. Okay. UV dominated will be the opposite case. If d is greater than 4, so say greater than 5, then gamma over h grows with temperature or drops as the universe evolves, and then the most dark matter would be produced at the highest temperatures achieved, sort of right at the beginning of the radiation down here, or right after reheating. Okay. And here I did this for 2 tube. It's a general property that higher dimension operators will lead to effects that grow with energy and therefore also grow with temperature and do a lot of high temperatures, and then things that are sort of marginal or renormalizable in the old language will produce effects that dominate at low temperatures. Yeah.
Are these IR and UV regimes relative to our EFT cutoff, or are we assuming the cutoff is way higher than UV dominated also?
I'm assuming I'm only ever talking about temperatures within the effective theory here.
Okay, got it. So UV dominated is still below like that.
Yeah, I mean, because then I would have to complete it. If I wanted to go to lambda, then this description, this language doesn't apply, and we'd have to ask what states occur there.
Gotcha.
You might then be dominated by production at that scale. It depends on the model. You could consider the case of the T reheat, the highest temperature achieved is below lambda, and then maybe you never probe the physics here. That's a possibility. Okay. Yeah.
I guess I'm not sure I understand why dominant production is going to be when that ratio is maximized.
Yeah, it's dimensional analysis.
No, but I mean,
like but I'll show. This will be I'm sort of jumping to the answer, so it's good that's not obvious, but I'll show example where Boltzmann equation will lead to this behavior. But if you write down a Boltzmann equation in terms of yield, then you'll find that you can write it as an integral over this thing. So you're sort of this integral will have most support when the integrand is maximized.
because like intuitively that makes sense to me. Gamma or whatever that is like a cross section more than a production rate.
But it has to be a rate by dimensions because you're comparing it with time.
Right. Okay, that's good.
Yeah, but this will be the behavior that comes out of Boltzmann equation, but I'm claiming you can guess this from dimensional analysis because it's the two time scales that you can compare. So sort of had to be, yeah.
Can't you just say that 1/h is the time that passed since the production began, right? So it's like time times rate.
Yeah, yeah,
And
exactly.
that's the
H is the
yield,
clock.
Basically, that's the yield.
Yeah,
So
exactly.
you want to maximize the yield.
Exactly. Yeah, that's exactly right. And then if you write a Boltzmann equation for the yield, you'll see this explicitly in the form of an integral with maximal support here.
Do you have some maximum data? Like in the earlier time, you have like a maximum of
Yeah, I mean, so the maximum will either be the highest temperature ever achieved, which would be the reheat temperature,
Yeah.
or it'll be, or you hit this cutoff and then this description breaks down. It'll be one of those two things. Has to cut, of course, it has to cut off somehow. Yeah, so it'll either be cut off by the universe or by the particle physics. Okay. But yeah, indeed, this makes it interesting. This case makes it interesting to talk about the reheat temperature, which I've sort of said various times in words, but the nice thing about thermal relics is you didn't care because you only care what happens at low temperature, but here you really care. So the reheat temperature, that I'll call T reheat, well, I'll define this to be the highest temperature reached by the standard model plasma. And this is model dependent. It would depend on your inflationary model and reheating model, like something like the inflaton decays into the standard model particles and then endows it with temperature, and then that would be the reheat temperature. And we don't know what this is. All we can say currently is it needs to at least be hot enough to give BBN. So successful predictions of BBN seem to imply that T reheat is larger than 1 MeV, but beyond that we don't know, and then sort of a parameter that you could contemplate that depends on your inflationary model. Yeah.
I hope I didn't miss this, or maybe you'll say it. But with this IR dominated, I mean, we'll just keep producing more and more dark matter, so there has to be something to stop us eventually, right?
Yeah, and what'll happen in practice is it'll be dominated by the mass threshold,
I see.
because when states turn non-relativistic, then they get Boltzmann suppressed,
I see.
and then that'll shut it off. So importantly, when these statements apply in this domain, and then the two boundaries will be what sort of stops things.
Is there any reason to assume that dark matter will be being produced after the heating and not during the heating?
No, you could have that too. Yes, that if it's during reheating, then that would be the initial condition from the point of view of these lectures, and then if non-thermal dark matter could be produced during reheating, and then that contribution you should sort of add to this this FIM contribution I'm talking about.
For these lectures, it's coming just from fundamental particles, right?
It doesn't. It could be psi could be a standard particle, or it could be a new particle like in a thermal hidden sector.
Okay.
But yeah, I'm assuming here it's thermal because I put a T cubed here, so I'm assuming it's some thermal state. But that's the only assumption. Yeah.
I think I don't quite understand reheat temperature. I would guess it would be T equals 0, right? Time of the Big Bang.
No.
Highest
T
temperature?
infinity. Big Bang high T.
Yeah.
Time. Your temperature. Sorry.
Yeah,
Time-
I guess, but
Time
T reheat
zero-
is the highest temperature reached by the standard model
Yeah.
plasma, right?
Yeah, which if you extrapolate is infinity, but in practice we only know it's some number above an MeV. That's all we know. So the universe cools as it ages.
Right, of course. I did mean time by the Big Bang. So at time equals 0.
Yes.
Wouldn't that be the maximum temperature?
Sure, but of course it's not really 0. It's some small number. So this MeV is another way of saying really we only know like that out to a second how the plasma acted, and then before that you need a model of inflation and reheating to specify, and that's model time.
Okay, so the
So 1
reheat
second is
temperature-
small compared to, so if you say the Big Bang happened at T equals 0, that's a good language only if you're comparing that time to time that's much longer than a second.
Okay.
If you're gonna say like if you're talking about recombination in 100,000 years, Big Bang was at 0, fine. But really, we only have resolution of a second in the sense that BBN happened.
Okay, so just to make sure I'm getting this, so the reheating temperature is like the highest temperature reached after the time of 1 second?
No. It's the highest temperature reached, and that's a parameter of the cosmology, which we don't know.
Uh-huh.
And when you say t equals 0, that's not so precise. That's a singularity in the F or W metric, but really something had to happen then. So it's like really Big Bang happened. You can say the Big Bang happened at t of order 1 second, or less than order 1 second. Just, and then if you want to go beyond that, if you want to refine what's happening on that scale, you need now model inflation or heating, and then you need to specify two readings.
I don't know if you talk about that, but could you have like a complex scenario, like weak and peak, or they are excluding each other?
WIM.
Yeah, because like thermal and non-thermal dark matter at the same time.
Yeah. So like I said, you could combine all 10, 15 different production mechanisms, and they could each give 10%, and they can all live happily together. So I'm sort of just for simplicity of language, focusing on the case that there's one thing making all the dark matter, but you can combine any set of mechanisms for making different fractions of dark matter. We only know their total energy density, and there could be different constituents, and some fraction could be like this, and some fraction could be set for whatever you want. Yeah.
And a follow-up question. How do you define the border between this freezing and freeze out? I mean, it depends on the strength of the interaction, right? But how do you?
It's a good question. I mean, technically, I would define it as whether the dark matter number density is far below its equilibrium value or not. And if
So
it,
one
so-
order of magnitude maybe.
yeah, and then there's some sort of gray area where it starts to thermalize, and there are even models you get where you sort of freeze into something that then thermalizes and then reannihilates, and you can study models that transition between these. But as long as the number density of dark matter is far below its equilibrium value, then you're sort of safely in this domain.
But otherwise you have like perturbation in the Boltzmann equation because you actually are equilibrium inverse processes. Right?
Absolutely, yeah. So when I said you can neglect inverse, I'm sort of always assuming n chi is much less than n chi equilibrium. And once you get close to there, then you need to consider inverse, and then you're sort of transitioning.
Like a posteriori, right?
Yeah, you should always check. Absolutely. Okay. So, where are we? Okay. Let me just say very quickly, I want to give an example of a UV type, and then I'll talk about IR types. Sort of a classic example is the gravitino in supersymmetry, because it interacts with standard model particles only through higher dimension operators. So you can have, this is one, there are many diagrams that could produce it. For example, you could have a squark and a quark. You're probably all too young to know what those words are, but making gravitino and a gluon. This is just one process. And these would both be thermal. And you're making this, and this vertex here is a higher dimension operator. It's actually, it turns out that it's a dimension 5 operator that has scale and 3/2. I'm fine. Over Lumino, and then you can plug that in to this expression, plug in T reheat here, and that would tell you the amount of gravitinos you make them. So one way that you can make gravitinos is this sort of UV dominated production, where the dominant production would be a T reheat. There are also other ways. That's sort of a motivated example of this UV production. Okay. So that's sort of all the general comments, and then the remainder of the time I'll talk about some more specific examples, and I'm going to now focus on the IR case, which is sort of more calculable in terms of low energy physics, so a little bit more connected to experimental tests typically, although the UV models can be fun too. Gravitino is an example where it's very, very hard. You cannot see it in direct detection or indirect detection, because it only couples through these really small operators. And you can though see like the other particles in the diagram, like the squark. Okay. But yeah, and just in general, the IR models tend to be more testable than the UV models because you're coupled through Ruderman operators. Yeah.
Was the purpose of that Gravitino example to show how we estimate the cutoff scale?
And just an example, just to
Okay.
people used to like Susie. Okay. Okay. Oh, cool. So we'll describe some zoology. I'm just gonna write some examples here, and then I'll kind of talk about as many as I have time to before we break for lunch. I don't think I'll get through all the ones that I'm able to talk about, but we'll just kind of talk about some. Yeah.
Before you start this, there's any constraints or ideas on how many gravitinos could be produced in this UV picture?
Oh, well, you need to, if it's all of the dark matter, then that predicts the amount. And you cannot produce more than the amount of dark matter we see, and that gives an upper bound. And in fact, this is really important. It's a powerful bound on supersymmetry models. Some of them, if the reheat temperature is too high, you would make too many gravitinos. And this is sort of a well-known challenge in supersymmetric cosmology, is avoiding overproduction of gravitinos. So sort of in a given model, where if you're in a model where you have UV production, that tends to often to give an upper bound on T reheat. Although experimentally we can only say it's bigger than an MEV, so those upper bounds tend not to actually exclude models, but they say, okay, if you want to consider this model, you have to be in a low reheat scenario. Yeah.
If the graphene exists, like they are actually dark matter, maybe they can exist outside of the dark matter complex.
Let me bring my neurons back 10 years. Okay, yeah. So there are models where it's heavy and it can decay. And then it's not a good dark matter candidate, and those decays actually have powerful constraints in them. And there are also models where it's lighter and very long lived. So it ends up that it depends on this things like the scale of supersymmetry breaking and the mass of the gravitino. So it is a dark matter candidate in general, but then you have to look at the details. Okay. So the most famous type of FIMP is named Friesen. That's probably what I'll spend most of our time talking about, and that would be things like the scattering that I've been talking about, although in a limit where you're IR dominated. And it can also be decay of thermal states, which will be IR dominated. So these things are called Friesen. Something related to Friesen, but different, that's new, actually by myself and others this spring, we call pandemic. I don't know if we'll have how much time we'll have, but here you actually also have a FIMP in the initial state, and this will give exponential growth of the number of dark matter scattering against the thermal state. Okay. Something called super WIMP, which I think Jonathan is planning to talk about in these lectures.
Yes, yes, beyond.
He's getting into my turf, but that's actually maybe good because I don't know if I'll have time for this. But here you have some thermal state that it itself goes through a WIMP-like freeze out, so maybe it annihilates, and then later it decays to the dark matter. This would be some other fine. And yes, it's this and then this. Yeah, sorry, here I mean or. So here I mean this or this. In super WIMP, first you do this and then you do this. And the difference between these two cases is this is occurring while this state is relativistic and equilibrium. In this case, you go through a WIMP freeze out, you chemically decouple, and then you decay at much later time. So the difference between these two is when the decay occurs, and then it's called Friesen or super WIMP based on that time. Yeah.
So for the Friesen case, you said that was for when we're looking at the IR dominated.
Yeah.
But I would have expected you to say the UV dominated, because when it's UV dominated, we're producing a lot at the beginning, then it cools down, and then we're stuck there. So whereas IR dominated, we start producing it later.
Yeah, and in this case, the dominant production will be when the temperature is on the order of the mass of this particle, which is often much heavier than the dark matter particle. So it's still like a dark matter is highly relativistic. But yeah, normally freeze-in refers to this IR dominated case. I have heard people refer to the UV case also as freeze-in. Personally, I don't like calling them both freeze-in.
I guess maybe I don't know what we mean when we say freeze in. I'm thinking that the temperature is dropping, so I can't produce it anymore.
Well, when we go through it, it will be clear, hopefully, but it'll be, the dominant production will be when the temperature is on the order of psi. The reason is it's IR dominated, so it's suppressed at very high temperature. And then once psi turns non-relativistic, it itself becomes Boltzmann suppressed and exponentially shuts all of this off. So therefore, the dominant production is right between those events, and then it's when this is semi-relativistic, when temperature is on the order of its mass.
Okay.
That's sort of a generic feature of freeze-in, that the production occurs at the mass thresholds of thermal states. Okay. Yeah, and then the fourth that I could talk about is the Olson-Woodrow mechanism for making sterile neutrinos, which is oscillations of active neutrinos, so E, mu, and tau, which are thermalized, into sterile neutrinos, where mixing angles seem to be small enough that this state is not thermalized and it can still be produced slowly. But now, sort of technically, you can describe it in terms of oscillation instead of a decay or a 2-2 process. Okay. So that's sort of some zoology. Yeah.
In this pandemic, dark matter as opposed to freezing, you need to have some initial amount of.
Yeah, indeed. You need to have some initial amount, or it doesn't happen. But then this exponential growth, so you're sort of not so sensitive to the initial amount anymore if this exponential growth happens. And the initial amount could be whatever from decay at reheating, or actually generically in these models, you'll have some small freeze-in production. So it's sort of a way of boosting the freeze-in amount to a larger amount.
I don't understand the super weak, because what is produced in the first process doesn't appear then in the second, right?
Yeah, it's just that psi goes through like its own WIMP-like freeze out.
Okay, okay.
Yeah, so like use all the methods that we learned for WIMP to estimate the relic density of psi, but then psi later decays to the dark matter.
Okay, it separates the two processes, okay.
Yeah, and then the number of dark matter at the end is just given by the number of psi produced by this annihilation.
Okay.
So you can just use your WIMP technology and then get the answer. Yeah.
Just to get an intuitive picture. So freeze out is like when essentially like universe is cool and expanding, and particles say don't find each other to
Yes.
keep the reactions going, and freezing is like when the temperature is not high enough to produce them.
Well, it's where they're made slowly. I'm gonna draw a picture in a minute that will help clarify the difference of the two. So maybe hold this question. Yeah.
On this, the superweb decay, is it decaying to a superpartner of the phi? Is that
Oh no,
possible?
I just mean a different particle.
Okay.
I don't know. What's another letter? A.
Okay.
I could have put another phi, but I just want to make clear that these things are unrelated. Okay. Okay, so I'm going to now discuss freeze-in in some depth, and then maybe the others you can ask me about, or we'll see how we do. But freeze-in being sort of the most famous and well-studied of these is worthy of coming first. It's an old idea, but it was named and generalized in an awesome paper in 2009 by Hall and others. But it has an old history. In fact, it's one of the ways gravitinos can be made. Gravitinos can be made, it turns out, in multiple 50 ways, and gravitinos can also be made through freeze-in. So the study of gravitinos production from freeze-in has a long history. But sort of the mechanism, this was appreciated as a general mechanism that you can apply to many things since this paper. Okay, and we're going to define freeze-in to be IR production of dark matter scattering or decay. Okay, and now let me draw a cartoon of the yield evolution to kind of show how this differs from freeze out. Yeah. Okay, so again, this will be the yield of dark matter, the number density per entropy, co-moving number density. This will be some measure of inverse temperature, although depending on the scenario, you might put different m's here. Now, freeze out, so that we're very used to this curve by now. You fall exponentially and then you become constant, and there's a moment of the freeze out. Okay. For freeze in, you normally would assume you start with zero abundance. That was one of in our list of assumptions, so that you could of course vary the starting point, and then the abundance will grow, and then sort of become constant. So this line is freeze out. This line is freeze in. You'll always be making some. It's just like the dominant rate will be at the time we said gamma over h is maximized, and then at some point the production will stop, and then it'll be constant. So and this is sort of a universal behavior. So freeze out starts with a lot, it dilutes, chemically decouples, done. Freeze in start with none, slowly leak in from the thermal bath until the leak in process stops. Okay. Yeah.
And so this freeze out moment where we get our relic, or sorry, for the freeze in scenario where we end up with our flat line occurs at this 1/m psi, I guess.
Yeah, it's when the dark matter, well, in the case of WIMP, annihilation is when the dark matter turns non-relativistic.
Right.
Yeah, and it's at this moment where n chi sigma b equals bubble, but in practice, this is satisfied when this gets exponentially suppressed and cross the mass threshold. Yeah. This flattening moment will in general be a different moment, which might make my cartoon.
Oh, I guess that's the one I was talking about for the freeze in.
Ah.
Earlier you said this transition would occur when m psi approaches the temperature.
Indeed. So that was why I was a little sly here. For freeze out, it's kind of useful to put an m chi here.
Right.
For freeze in, you would actually normally put an m psi here, and then if you do that, then this would be an order 1 value. Okay. So let's carefully analyze a specific case. So let's consider freeze in from decay and write down a Boltzmann equation and see what happens. Okay. So Boltzmann equation for the number density will take us to the general form. This applies to all FIMs and thermal relics. Then the question is, what's the form of this collision operator for decay? And here in the FIMP limit, we only need to consider decay and not inverse decay. Generally, they both be present. But actually, I'll show you what both terms look like for the hell of it. And this will give us a chance to also introduce the concept of thermally average decay, which we haven't talked about yet. We've met thermally average cross sections, but there's also thermal average for decays. So this will the integral collision operator will go like thermally averaged decay rate of psi, psi equilibrium, and then there'll be a term with a minus sign that describes the thermally averaged inverse decay. And then you can, as usual, use detailed balance. And then after you do that, you get the following expression. And in the FIM case, we assume this starts at 0 and always has a number density far below equilibrium, and that's why we can neglect the inverse decay. So as long as n chi is much less than equilibrium, we can neglect this term, and then there's just one term. And then we're just solving the following equation. Here I'm assuming the psi state is always given by its equilibrium abundance. Okay, so this is sort of the Boltzmann equation you want to solve for FIM production from freeze in production from decay. And let me now define for you what this object is. And it's really analogous, just like for like thermally averaged annihilations, it's like a regular annihilating cross section, but then you integrate over the phase space of the initial states, and it's the same idea here. It's like a regular decay rate, but integrated over the phase space of the mother, weighted by its distribution function. That's what the thermal average is doing. So this is given by integral over Lorentz invariant phase space of mother and daughters multiplied by phase space distribution of mother, matrix element squared, times as usual the delta function, then it goes energy momentum conservation. And it turns out that you can do all these integrals analytically. And then you get although the answer, well, when you do it analytically and plug in equal phase space, it does give you some nice Bessel functions. Of type 1 divided by Bessel function of type 2. If you're not so familiar with these things, Mathematicon knows exactly what to do with them. And well, I'll just report to you the limiting cases where this is either much bigger or much smaller than 1. So whether psi is relativistic or non-relativistic, and then you can then this will simplify. So this will become psi over 2t. I'm assigning the limit where psi is relativistic, and just the usual decay rate limit for psi is non-relativistic. So you see, you get a suppression at high temperatures in a thermally averaged decay. Does anybody want to take a guess at the physical origin of this suppression?
Yes, question.
See, this is suppressed. Like at low temperature, it's just like the regular decay rate that you're used to. At high temperature, it goes like m over t. So the decay rate is suppressed at high temperatures when you're in this thermal bath. So what's the physical origin of that suppression?
What's going on? IR dominated.
I think I heard the right answer. Lorentz. It's just the time dilation. So once the psi are moving relativistically, then their clocks change, and then that's encoded by this pretime.
Explain the factor.
No. But would you? You're an expert physicist. There must be a good.
I'm sure there is. That's why.
No, I don't have to. Okay.
Sorry.
Yeah.
In your expression for the thermal average decay width, there is a factor of 1 over mass.
Oh no. Yeah, you're right. Thank you. But it's not mass, isn't it? A 1 over number density cube.
No, 1 over mass of the psi part.
Sure.
The factor in the center of mass of the psi.
Okay, I'm not willing to take a firm stand in real time.
No, in the pipe you have the.
Yeah, actually, I would have guessed it's 1 over n psi equilibrium.
I mean, the d pi has dimension 2, 4, 6. The delta function has -4. We are left with dimension 2. We need to divide by 1 over mass.
Yeah,
1 over 2 times the mass. Yeah.
I definitely believe you.
I mean, you have the incoming particle, so you have to take the time factor.
Yeah, and when I get confused, I look at the appendix I told you for thermal averages. And I will see if I can salvage it in 30 seconds, or else we will do it offline. Oh no, this is not going to be a 30-second jump. Yeah, indeed.
So before you thermal average, you already have this one.
Okay, we'll have to do this after. I can't do this in real time. Okay. Yeah, what I'm sure is that this step is right, and this definition may be missing a prefactor, I can see. Okay. So. So we have the Boltzmann equation. And this actually takes a simple form if we write it as a Boltzmann equation for the yield, which is going to be useful. So I'm going to now change variables to the yield of time and the inverse temperature in terms of the psi mass. Okay. And then we can write y chi dx. Actually, better yet, d log x. Y psi equilibrium times our thermally average decay rate. Divided by Hubble, although it's a little subtle, I'll call this Hubble tilde. This is going to equal Hubble in the limit where G star is constant, where G star S is constant, but when they're not equal, there'll be a slight difference. This is going to be 1 over, sorry. Oh no, it's the denominator. Minus 1/3 d log G star S d log x. So if you want to be careful, it's shifted from Hubble by a small amount. If G star S changes, and it's a good approximation to just set this thing equal to Hubble, except like if a very large number of degrees of freedom are decoupling at the same moment, like during QCD phase transition, then you want to keep track of that difference. But for sort of simplicity, I'm going to now neglect the tilde and just take G star S as a constant. Yeah.
I don't understand why Hubble would be changing at all. I think I missed
Oh, no, Hubble is Hubble. It's just that if you change variables to these variables, then the differential equation doesn't have Hubble in the denominator.
Okay, all right, thanks.
Yeah, and it's just coming in order to get this to look simple. Otherwise, there's an ugly prefactor that comes about when you do the change of variables. Okay. So then you can just integrate this to get the yield, but to understand when the yield is dominated, we should ask about the behavior of the right-hand side.
I just want to make sure that they see what.
Yeah, but I need to look at the screen too. Yeah. Okay. So you want to look. At the behavior of this, and I'm just going to single out the temperature behavior. So this is proportional to the decay rate of psi times temperature to the -3 at high temperatures. Okay, so legible. Where did that? Because there's a t squared from Hubble, and then there's a 1 over t from the thermally average decay rate. So you get t to the -3, and then once the temperature drops, and sorry, this is m psi. Once the temperature drops below m psi, this becomes Boltzmann suppressed, and this gets exponentially small. So then the prefactor doesn't really matter. The important thing It's just, it goes E minus m psi over T. The temperature much less than m psi. So if we make a plot of this thing that's determining the production, as a function of inverse temperature, say it's a function of m psi over T, it's going to rise and then drop very quickly from the exponential. And then the peak will be somewhere a little past 1. Maybe again, something like 3 to 5, just to give some time for the exponent to kick in. Yeah, so we call this 1. So and this is kind of the general property of IR domination typically. So we said before when we said we were only studying this regime in our IR versus UV discussion, once you cross mass thresholds of equilibrium states, they get exponentially suppressed, and then that shuts things off. So then the dominant production will be when m psi over T is order 1. This will be when the right-hand side is maximized.
So we managed to write the equation, the Boltzmann equation in terms of the number density. So how is it possible given the fact that the dark matter never reaches thermal equilibrium?
Well, you start with the Boltzmann equation for the phase space density and then integrate it, and then that's the number density. But here the phase space distribution is not the equilibrium one.
I thought we would only integrate out the dependency momenta when we are in kinetic equilibrium.
For the in general, that's true, especially when you're dealing with like thermally average cross sections and things like that. But just the left-hand side of the Boltzmann equation, you can just do the integral and you'll get n. In general, just because for any distribution, n is defined to be given by an integral over d through df, whatever f is. So you can do one integral, and then the left-hand side will be the usual. But importantly here, f it could be very different. It turns out in this case it's not too different, but people have done careful studies where they actually work out what f is, and it's interesting.
Sorry, because here psi is in equilibrium, right?
Yes.
Okay.
Yeah.
Psi was not in equilibrium, I guess we could not write the equation with rho.
Yeah, and then this thing would be different.
Okay.
So something must be producing our psi as always decay.
Something
else must be producing psi.
Yeah, I'm assuming psi has an equilibrium distribution throughout this process, and that requires other interactions that maintain that equilibrium distribution. And when I said when I'm plugging this in, I'm also assuming it's in chemical equilibrium because I didn't put a mu here. So there have to be number changing interactions faster than Hubble that involve psi. Psi could be a standard model particle like the Higgs boson or whatever, and it has maybe other rapid decays that are faster than Hubble. So it's like thermodynamic properties are determined by other rapid interactions, and then some small fraction of it is leaking into chi, which is all we care about from chi's point of view.
Right.
Okay. Any other? So, sorry. Yeah, so we conclude from this whole discussion with the dominant production that's of order m psi because of this, and then we can actually perform the integral. And then the sort of final abundance that I'll call freeze-in, so sort of at infinite time, will be given an integral from 0 to infinity dx over x of this object. In here, I'm neglecting the tilde, so I'm taking G star S equals constant. And by 0, I really mean whatever initial condition you want, which should be some temperature much higher than psi. And by infinity, you can actually replace that with any time, and then this would give you y at that time. But if we sort of after the exponent, it shuts off, so sort of putting in any time, any like such a temperature is far below the psi mass would work. And then if you do this numerically, we'll find the following. Sorry, so this is number of degrees of freedom of psi. You get G star S and a G star from where entropy entered in here, Hubble enters here. The ordinary decay rate appears here now. The Planck came from Hubble. M psi squared. Yeah, and you would have sorry, up to an order 1 number, you could have just estimated the back of the envelope version of this would just be that y chi is of order gamma over h evaluated at t equals m psi. That'll give you this expression. So that was sort of the intuition for why gamma over h dominates. But yeah, and in general, for the same, it will actually apply for 2-to-2 reason, where this now becomes the rate, so number density times cross section over Hubble, again evaluated at the mass threshold. So this sort of the yield is rate over Hubble, will be the general property that you find from carefully doing these Boltzmann equations. Okay, so let's apply this to look at a specific numerical example and kind of get a sense of what coupling size works for Friesen. Okay, so let's take a scalar to be the mother. And I'm going to take it to decay to dark matter and anti-dark matter, which you could take to be a Dirac fermion that couples through a Yukawa interaction. And now, since each mother decay produces 2 dark matter, you should multiply our prior discussion by a factor of 2, or equivalently, the prior discussion would have applied separately for the yield of dark matter and anti-dark matter, and you add them. Okay. So here, the decay rate is just y squared ms over 16 pi. And now let's just do a numerical example. I'm going to take ms equal 1 TeV. And then at this value, G star equal to G star S. But here I'm just including the standard model contribution, and then that's 106.75. You could add 1 degree of freedom for S. It's only going to affect things at a percent level. Yeah, and the number of degrees of freedom is just 1 for a real scalar. Okay, so this is some Higgs-like thing decaying to a fermion. Okay, and then to match the observed abundance, we want m chi, y chi. So remember, this should be of order T equality. The careful value was 0.44 eV. And then you can plug in this expression for y chi on this side, plug in this value of gamma, and then you can ask what is the yield as a function of the Yukawa, and you find that this equals about 10 to the 11 y squared mf, sorry, chi over ms. Because you have an m squared here, but then 1m comes from the decay rate, so you get a 1 over ms. Okay. And now if you just set this equal to this, we conclude that in this case, the Yukawa should be about 5 times 10 to the minus 11. And well, here, let me restore the dependence on the masses in case you want to vary that. So here we have m chi, which I'll normalize, say, to a GeV. Okay, yeah, and here Like I use these values of G star, so if you want to vary this to be much lower, you should pay attention to the G stars. But anyway, when you see this very small Yukawa will give the right amount of dark matter. In fact, this tends to lead to lifetimes that are often too long actually to look for in colliders, though there are certain versions of Friesen where you can look for them in colliders. So you could look for sort of long-lived decays with this test. Yeah, the units have definitely broken down. This is not good. What have we done?
Why is it broken? Shouldn't it be dimensionless?
Yeah, no, I'm setting this to EV, so this is not so healthy.
Why you cut them?
Yeah, why is my coupling? Why is dimensionless?
Oh,
It's Yukawa. There's an M Planck missing. So this is GeV. I mean, you're right. This must be GeV. Yeah, sorry. Yeah. Okay. Oh no. That is all I want to say about Friesen. So I think the rest of the zoology we will have to leave as a question. Jonathan will cover these. These I can tell you more about. This will be a similar Boltzmann equation. But now to the Friesen case, but now the kind initial state will actually give an exponential growth. So you start with some initial condition, and for this sort of Friesen from decay, you're growing kind of steadily. For Friesen from production from pandemic, you would just have a sudden exponential growth, which can be cut off if you hit this mass threshold. So it's about
Questions for? Are there some kind of production in the red waterfall?
yeah, you could do the psi could be a standard model particle in general.
Yeah, but there are some particles in this kind of model.
Sorry.
There are some kind of standard model particle where it's produced by using
Are you asking or? Well, yeah, the standard model particles, they're all thermalized already, so they would not be produced by Friesen. Because they sort of all start with large equilibrium number densities, because they all interact with each other by a large amount. Yeah, Friesen would only apply to something that's completely kinetically decoupled, so that you start with none and then leak into it. But the standard model is all coupled to itself so strongly that it all equilibrates initially.
you say that
Yeah, you can look. There are studies looking for long-lived particles associated with Friesen and colliders. It tends the dark, because of this small coupling. It tends to be hard to look for this directly. This type of scenario is very depressing for direct detection or indirect detection. So your kind of best hope is really to go after that state, and maybe also go after this decay process.
last question.
Yeah, very fast. That's a question that always puzzles me. Like in a complete model, you have this S maybe that's coupled to some particles which are lighter because you want to keep S in equilibrium.
Yeah.
But when you like finish to, I mean the yield of S is exponentially suppressed. You basically are integrating out this S, but then you can generate an higher dimensional operator, right, with those other particles which couple to S and disguise.
Yes.
So in this case, Friesen is explored or not?
That's a good question. Yeah, indeed, there would typically be other channels. So by saying when I'm saying Friesen by decay, I'm sort of simplifying to assume the decay is dominating. But yeah, indeed, like suppose I now add some other state that is keeping S in equilibrium that I call phi, and this is faster than Hubble. Then indeed there will also be a 2-to-2 production of phi through an S. To Kai's, I think this is what you're asking about.
Yeah.
And then you should also look at Friesen from this and add the different contributions, make sure you don't double count. And then,
So
and it depends now on where you are in parameter space, whether decay or
if I
scatter.
don't consider this phi existing, I mean, am I forced to consider this phi existing and also this other diagram?
Well, you could, in general, you could actually have 3s to 2s maintaining equilibrium, and then there's no other state.
Mhm.
So it really depends on what is keeping s in equilibrium.
Okay, so it might be in equilibrium with itself,
Yeah,
but itself, like,
yeah,
that's fine.
that would constrain the mass scale in order to keep this fast. It would things would have to tend to be light, but yeah, it depends on the details. And indeed, when I'm saying I'm doing Friesen from states in equilibrium, then I'm sort of purposefully not discussing it's a good logical question, what interactions are keeping them in equilibrium, then applies to interacts with other states, and therefore the dark matter also interacts with other states, and then can those states directly make the dark matter? And that type of question you need to ask in every model. But there are models where a simple decay, like I'm highlighting, is the dominant contribution, but it would rarely be the only contribution, and you need to identify all contributions and then correctly
So
find the biggest
If I
one.
want to say just general, I can just be agnostic about that and do not consider anything, right? If I want to be just general and do not specify a model where you have, for example, 2 you have as like in this case.
I'm not sure I understand.
The point is that if I want to be just general, can I do not specify the interaction and just say that the decay dominates?
That's an assumption,
Okay.
but you could make it as sort of a universal subset of the bigger model space.
Okay.
Yeah.
But it doesn't spoil the general. I mean, it doesn't happen always.
It won't happen always, but it will describe many different limits of more complicated models where interactions are keeping us in equilibrium.
Some might be just perturbations to the final result.
Yeah, but you need to be careful, and it really depends.
I see, thanks.
Well, thank you, Josh.